It's okay? Okay, great. Yeah. So this talk sort of works really well following Bob's. And in part, Bob and I, he's been one of the most influential people in terms of my career and such, and learning from him has been great. You know, it's funny also to be back here because I got my PhD 25 years ago in August from this place. And, you know, if I'd gone to a different place, I don't think I would have done structural work. You know, I'm pretty sure that if I'd gone to Chicago, I would have worked with Steve Levitt. But by coming here, I ended up going down a very different path. And I still remember wanting to do effectively a dynamic discrete choice model, but I wouldn't have been even able to articulate that that's what it was at the time. And John Rust was teaching the second year econometrics class, and we were supposed to tell him about our paper ideas. And so I went in and I explained my paper idea to him, and he said that he thought he could help me out with that. And I said, you don't understand, it's a very hard problem. It's a dynamic discrete choice problem. And he was very kind because he'd actually already developed techniques to do exactly that, you know. And then got hooked up with Bob on the unobserved heterogeneity and CCP stuff. And I didn't really know CCP estimation at the time. And I'd call him up and I'd say, oh, I'm so excited, you know, with CCPs we can do this. And Bob would very nicely tell me, yeah, we'd already did that in Altug and Miller. Some of the times that was even correct. But so I benefited from people who were very patient with my lack of understanding of what had already been done. But now we're going to piggyback off of what Bob did to talk about doing this stuff in continuous time and show that some of the same things he was talking about actually apply in continuous time and in some sense in easier ways. I think people should be doing continuous time way more than what we see in the literature. Now, but I think that's partly the guys working continuous time's fault, as I'll say in a little bit. So when we think about continuous time models, what's different about that is you often think about these things in terms of hazard rates, right? And what I want to do in this talk is think about that, but in the context of dynamic discrete choice models in the way Bob was talking about it. The main difference is going to be is that instead of thinking about people making decisions on January 1st of every year, those decisions that come at you following some Poisson process. Okay? But key is you're still going to get those nice errors that make everything convenient for you when you make your decision. So the way this is going to work is that we've got these hazard rates, and those often depend on some observed characteristics. I'm going to decompose that so we have a move arrival, lambda, that's going to dictate when you get to move. Okay? And then once you do that, there's going to be some probability that you make a decision. That probability make a decision, it's probability from the perspective of you in the sense I don't know what my future preference shocks are going to be. But from the perspective of the econometrician, I'm not going to see your current preference shock as well. Okay? So the hazard rate's the product of the probability move times the probability that you make a particular decision given that you had the right to move. If you set things up in this way, all that framing of the value function stuff that Bob was talking about is going to still apply in continuous time. Just the forms are going to be slightly different. Okay, so we'll see what we mean in a second. So starting in a single agent case, we're going to have time be continuous, finite state space, and now we're going to be thinking about two competing Poisson processes which can change the state. The first is the exogenous stuff, right? That's going to be this KL. That's the rate of moving from state K to state L. That's happening just because nature's doing its thing, okay? But then you can change the state if you have the right to do that. And lambda dictates that. And you can choose from these, some set of things. Now, framing it this way actually puts you in better shape for actually restricting the number of choices you might actually make. So, as an example, if you were doing dynamic discrete choice move once a year, then you've got this issue where you see somebody build, you always want your choices to encompass everything that could happen, right? So I could build 5 stores if you see somebody build 5 stores in that year. Here it could be, well, they only had the chance to build 1 store, but they got that chance multiple times. So you could actually restrict things there. But the other thing about going from continuous time is you actually end up with we're going to have a distinction between 2 parts of the utility. The first part's going to be an instantaneous payoff for taking an action. And that is where we're going to put in this epsilon at the end, okay? So a natural thing would be in the bus replacement, right? So with the bus replacement, we got the cost of replacing the engine, and that's going to be where that error is. Happens to be there's a nice sale on bus engines, right? Or not. But then you're running the engine, and that's going to be your payoff. And over a particular period of time, we're going to get some payoff. This is my flow payoff UK. And then you're integrating out for this period of time for how much I'm going to get with some discount rate rho. This makes it seem like I'm going to be doing lots of integrals. We're not going to be doing lots of integrals, and that's the way we're going to set things up. Okay, but that's an important distinction here. Just to preview, you really want this epsilon on the instantaneous payoff, so you don't have to keep track of it going forward, which is exactly what you've got in the dynamic discrete choice case. Those epsilons are nice and independent over time. And to the extent that you're worried about that, well, then we'll put in some unobserved heterogeneity, and that's permanent or something, and deal with that. Okay. So at this point, you're thinking, well, this just seems like it's making things more complicated. Okay? But it's going to work out quite nicely as we go along. So let's think about going from discrete time to continuous time. V of k, that's going to be the present value of lifetime utility given initial state k. So I'm in that state now. I don't get to move right now. I'm in that state. And I know I'm going to behave optimally in the future, at least in an ex-ante sense. Like given whatever comes at me, I'm going to make the right decision. But I'm forming expectations about the future stuff as I'm going along. I'm making it too complicated by saying let L of JK give the state, conditional on making choice J in state K. That makes it more complicated, really. Is, when you're in continuous time, things aren't happening at the same time anymore. So I really have lots of control over the state, right? If I have a bus engine and I replace it, I know I've got a new bus engine, and I know exactly what mileage state I'm in continuous time, right? So if we think about the way this value function is going to work in a short time interval, I'm going to get UK for having that bus engine. And then there's going to be some probability that the state changes in that short time interval because of what nature's doing. That's that QKL part. Then there's going to be some probability I get to actually make a decision. That's the lambda part. And if I get to make a decision, I'm going to make the best decision I can, which is the Emax, right? And that Emax is just integrating out over the epsilon, okay? Now notice what happens in continuous time is you're separating out transitions that are happening on what nature's doing from transitions that are happening because of what you're doing. You've broken out the two pieces. Now, over that short time interval, maybe you both had a chance to move and the nature might move in that short time interval. But if you keep shrinking it enough, that's not going to happen. Okay? So this part here is probably that nothing happens. So you think about that time interval being sufficiently small that this probability, that it's actually a probability, so that the number here is less than 1 minus this is going to, that numerator is less than 1. Okay? Between 0 and 1. We don't want it to be negative. And in that case, I'm still in that same state K. Everybody with me? Any questions about this? I want more questions than what you asked Bob. Seems like it took a little bit of a while to get warmed up to us. The point is to have you understand this. And so if we're confused here, we're going to be in big trouble later. So ask the questions. Okay, so the whole idea is in that short period of time, there's some chance nature's going to move, some chance I get to move, and some chance nobody gets to move, in which case I'm staying in the same state. All right, so what are we going to do? Well, I'm going to take those VK terms, there's a VK on both sides, take them, put them on the other side, okay? And you're going to end up with this thing here on the other side. Once you do that, now at that point, there's no longer that 1 there. Everything has a delta t on it. So what we're going to do is divide by the delta t, and then we're going to take delta t to 0. If you do it in the right order, magically everything sort of works out nicely. Go for it.
In principle, the arrival rate of the Poisson process might depend on the state K, and that equation will be exactly the same, no?
Oh, exactly. Yes, you could have that. Yes. We're going to make it simple here. Yeah. And that gets really, I want to come back to that. I think that works out great when you actually see move times. If you don't see, like, for example, buying a house, for example, you see the rejected offers or something. Then you might be in business to be able to actually distinguish the lambda as a function of the state. It gets a little tricky to think about distinguishing it.
Of course,
But that could be lambda k, and there'll be no problem at all. Thanks. Yeah, that's right. Okay, so when you move it over to the right side, then you divide by delta t. Once you divide by delta t, what I want you to see is I'm going to have a row here, the sum of the rates here of nature moving, and then the lambda, okay? All that part is going to go in the denominator once I divide through by that. And you end up with your value function for being a particular state k as the flow utility of being in that state. We got the transition probabilities that nature is going to do, and then you got the plus the lambda Emax thing, right? All over the sum of those rates. So just by putting in this error in the model, you could then, given these values, we could actually solve using a fixed point algorithm. We take expectation, we have a particular functional form for those epsilon j's, right? And you can just solve away, okay? We can actually simplify this even more with CCPs and such, but this problem actually is not going to be so bad, and it's nice and linear. And note that we've separated out, the big key with the continuous, one of the benefits of continuous time is you've separated out your choice part from nature's part. Okay? Go for it, Rasmus.
Just there's a little trick in this particular setup about how to turn this problem into a contraction mapping problem. As it's stated, you have to be a little bit careful to just run straight into. Are you going to talk about that, or?
I'm not.
Okay, but then just a slight warning to people. If you think you should just contract on this, this isn't necessarily a contraction mapping. You have to apply a little trick, but this is definitely doable.
Yeah, that's a great point. And actually, I think part of the reason I glossed over that is I'm going to actually try to avoid the contraction mapping altogether.
Perfect.
Okay. So there's a lot of things about whether we're going to call it the conditional value function or the choice-specific value function. This nice thing about working in this setup, you're just working with the value function. Okay? This is the value of being in state K. That actually has big implications for when you think about trying to get finite dependence to work out and such, because now things are going to be in terms of the value function. Okay? So what's nice about that, now let's think about, well, what are the choice probabilities? We got our value function. Now suppose you actually have the right to move. What's going to happen? Well, I'm going to choose, my decision rule is, I'm going to get these instantaneous payoffs. Those instantaneous payoffs depend on my choice and what state I'm in, potentially. That error associated with that choice, and then that value, my value of what state is going to result from making that choice. So that could be I built another store, in which case I have one more store. Or it could be I have a new bus engine or whatever. But I know where I'm going on the basis of that. We could make it uncertain, like I make a choice and then boom, something random happens. Most of the time, we don't even need that, right? That's not how that's going to work in this continuous time setup. I built a store. So then we have our choice probabilities, and we're going to have that thing be nice and type 1 extreme value. Then we know what we're going to get here. We have a logit probability. Okay? So right now, when we're thinking about continuous time, you're still ending up with these logit probabilities here if you assume that when you get a move arrival, we're going to have that random component to it, just like you would in discrete time. The big difference here, again, just is my move times once a year, or if I have twice yearly data, once every 6 months, or is it this plus on arrival process? Okay? So, when we think about these terms, what I want to do, I got value functions on both sides. I want to get rid of them. If I can get rid of them through functions of like conditional choice probabilities, now I don't have to do that contraction mapping and worry whether it works or not. I'm all set because I'm just going to plug in those adjustment terms that Bob was talking about a minute ago. Okay? It's funny because when you think about where all the problems in dynamic street choice come from, it's through the Emax term, right? Emax term is the easy thing in continuous time. We're going to get that like right away. The harder work is actually getting rid of that VL term, okay? All right, I make it too complicated here by these gamma functions. Reality is, I want you to think about this in a logit world because it's just so simple to work with, and then the adjustment terms are really obvious. And I will show you those in a minute, but it applies more generally. And it rests really on what Bob was already talking about, which is that the Emax term we can always express as relative to one of the choices. We're just going to factor out that choice, one of the choices, whatever choice we like, right? And then the value of that choice, like pre-committing to or whatever, we're going to get that term here, instantaneous payoff plus the value being that state, plus an adjustment term. And that adjustment term only depends on those CCPs and what choice you're making that adjustment term relative to. Okay? So what is that going to buy you? Well, I mean, just as an example, if there's a choice to do nothing, what are you going to get? Well, at that point, the term you factor out is the VK there, right? And I'm saying there's no instantaneous cost to doing nothing. Okay? We could put that in there. I'm not sure how well it would be identified. But so our Emax term, just to be clear, became that gamma 2 function plus lambda VK. Okay? That gamma 2 function is going to be minus log probability of the choice. That's what's always going to do with these logits. Plus the lambda VK. Well, now you can see why it actually works great, the Emax term in continuous time, because that VK is the same as the VK over here, right? So I can put it on the other side, and what it works out is then the lambda just disappears from the denominator, and you end up with this expression here. Okay. So we just dealt with the hard part of dynamic discrete choice in terms of getting rid of the Emax. We're still left with the value function here. Okay? Now I'm going to be doing some of the same tricks, so if you're like, that doesn't make any sense, this is the time to say that doesn't make any sense. Okay? It's possible that repeated things that don't make sense will make sense. Okay, but you see the setup. The name of the game is get rid of these, right? Really, that was the name of the game in Bob's thing as well. How do we get rid of the V's? We do some substitutions. So it's a function of U's and choice probabilities and F's, the transition probabilities on the observed states. Those F's in Bob's are the Q's here, and they're separate, right? It's not entirely right because my choice affects the state, but it does so in a deterministic way, so you don't have to worry about tracking it. Okay, so we got rid of the Emax term. That was actually easy. Now we want to get rid of the VL term. And this is come back to Rasmus's question about finite dependence. And I'm going to go through like gory detail about how it works in this context with examples. That was actually the great thing about working with Bob. Bob sees things like at a higher level than I do, and then I've got to like reduce it down to examples that I can handle. All right. So how are we going to eliminate those right-hand side value functions? Well, now we're going to go back to Hodson-Miller, and we're going to think about ways of taking those value functions and linking them. Well, how would you think about linking the value functions, right? Well, if you go back, it's the inversion. Value functions are linked through the conditional choice probabilities. This is the conditional choice probability. It'd be nice if I actually used the same notation, but it's a conditional choice probability. This is a probability I make choice K in state K. And that depends on these instantaneous payoffs and the value functions associated with the states that will result from those choices. So when Bob was doing his inversion, he was going to get differences in conditional value functions. Here we're going to get differences in value functions of being in particular states. Okay? This is our linking function. Okay? So any place, any time that I can get from one place to another through this function. So our proposition here is that the value function for being in this state, we can get there, link it to a value function from some other state, provided that there's a choice I could make that will put me in that other state. And then we just have an adjustment term, okay? I don't think that's going to be very clear until you see sort of an example. But that's the idea. We can put you, if I can get there with one choice to another state, then I can link the value functions associated with those two states. If I'm in state K and I can get to state L by making a choice, I can link those things through the conditional choice probabilities. And now, turning to the finite dependence, and we'll go through gory examples of this so it's actually clear. There might be maybe I can't get there right away, but I can do a whole series of linking, right? So I think Bob mentioned that investment thing, like by taking an investment action, maybe I can't exit the next time. But maybe after that decision, I make some other decision, which allows me to exit, and so then I can link you. So as long as a state's attainable from a particular state, like through a whole series of choices, I'm going to be in great shape. Now, when we think about that in the context of dynamic discrete choice and say, well, a whole sequence of choices, in dynamic discrete choice, every time I make a choice, some F is going to take me out to some other, you're effed, right? Because those transitions take you to other places. Here, you don't have to worry about that because I can just link it through a series. You don't want to think about this actually happening. It's just a mathematical expression of if I'm in this state, I can link it to another state through this choice probability, which can be linked to yet another state through this choice probability, and through a whole series of them, I'm set. So finite dependence, and I'll show you some examples of this in a minute, finite dependence is actually easier in continuous time than it is in discrete time. Go for it, Rasmus.
Are you free to also consider collections of states in this argument?
So what do you mean by that?
I'm formulating this as I'm thinking about it, but suppose that you have a continuous state space. This becomes sort of problematic to think about.
Definitely.
But the way that I would then try and get past the continuous state space is that I would think about sets of states and the value of being in a set of a space. If you can think about such a thing, and once you've done that, thinking about running into a state would then be this set that you're wondering about. It seems like this would be valuable if you had freedom to define sets of states.
Yeah, I'd have to think about that a lot more. It actually sort of relates to when can you get finite dependence and when you can't.
Yeah, no, exactly. And so, like, if
with
the idea
dynamic
is that
discrete choice, with a discrete choice, you're almost restricted onto a discrete number of states that you can go through it being a discrete choice.
Right.
So an example where it doesn't work as well in dynamic discrete choice, and would be true for here as well, is like if you thought about human capital depreciating at a particular rate, because then it sort of takes you off the grid. You could handle human capital depreciating by keeping it on a ladder and saying with some probability it bumps you down one rung on the ladder.
Sure.
Then you can still get the finite dependence. But if it depreciates like at a rate of 5% or something, well, I can't get 0.95 units by making one choice. And that's actually does come back to Altug and Miller, because he says if you stay out of the labor market long enough, then it will reset. Would be how he would get finite dependence in that.
Thanks.
But yeah, discrete states sort of works well from the purposes of making the finite dependence work, because you can line up the states the way that you want.
When you're practically doing this, you're likely discretizing your state space in some sort of fashion. You're making judicious choices on the front end of how you're going to make this tractable, right?
That's right. I mean, it's interesting to think about, when we get to the paper that I'm going to present on Wednesday, there are ways to think about these things in the limit, in terms of like wages, for example, being something that might be continuous. But then you have to be careful about what nature's doing, as long as nature doesn't move you around. But you could still have some probability of, in the limit of getting a particular offer.
All right, thanks.
All right. So the forms of these, so we have all that linking stuff. Well, the forms are actually really simple. If we have type 1 extreme value errors, you just take the ratio of those choice probabilities, and you end up with the ratio of the EXPs of the payoffs, right? That's the instantaneous payoff for taking the action, plus the value function for the state that will result from that action. So if you take that ratio, now you can see why I ended up with these size difference like that. It's just going to be the difference in those log probabilities. Starting to look a little bit like an IO talk, right, with the inversion right there. So we know we can do that linking there, and then Emacs term was simple. These form the basis for how you can get everything set up in terms of conditional choice probabilities. Okay? All right. So still not getting any questions besides from faculty. But maybe the example that I'm going to grind through will make it clear. So the way you could think about this example is slow adjustments. I'm going to make it tricky because your option of doing nothing I'm going to label as 0. But I stupidly labeled the other choice as -1. But the idea is that suppose nature moves, and they can increase the state from 1 to 10 units, okay? But when the agent moves, you can only decrease the state by 1 or do nothing. So clearly I can't, if nature goes up by 10, I can't get to 10 right away, right? But the way the problem is set up, that you don't have to worry about that, because I can write the linking functions to connect a state 10 ahead to my current state. Okay? So what's my goal? My goal is to make substitutions with conditional choice probabilities so that all the V's, the one here and here, are gone. If I do that, my problem only depends on flow payoff parameters, which are the U's, and then these rates, which we're going to estimate ahead of time, just like the F's. Okay? And the lambda and the instantaneous cost of changing the state. All right. So the first thing is, if you have logit errors, right away I can wipe out the Emacs term, because I just have them do nothing. I normalize the Emax term relative to doing nothing. That's all that math here. You know, when you have that lambda log of the sum of the EXPs, that's my expected value that's my Emax term, right? With that probability here, I end up with just minus log the probability of making that choice of doing nothing plus lambda times the same VK that is over here. Then when I rewrite it, that lambda VK effectively cancels with the lambda here, and we've got the expression here. So again, the Emax term is the easy one, and this is Euler's constant. We don't actually have to worry about that because in estimation, we're going to look at differences in these V's, and that part's going to end up canceling anyway. Okay, so what about the VL? Okay. We're going to want to express those future ones, VK plus 1 through VK plus 10. It could go up 1 all the way up through 10 as functions of VK plus whatever the adjustment cost is, the C. Well, I can always link one to a value function with one lower state, right? Because I get to decrease the state by 1. So if we think about L being from K plus 1 to K plus 10, if I think about the value of being in state 10, I can write that as the value of being in state 9 plus having to pay the cost of decreasing it, and then the difference in the log probabilities between decreasing the state and leaving it where it is. I can link it all the way back to VK, just keep going back. Once I have an expression with V9, I can link V9 to V8, V8 to V7, all the way down to whatever the state is that I want. So for any of those states L, from K plus 1 to K plus 10, I end up with the value of the state that I want, which is VK. If I can frame it in terms of VK, I'm set, because then I can take it to the other side. VK plus how many times do I have to make that decreasing the state? That's L minus K times C. And then the difference in the log probabilities. So if you substitute in for VL and rearrange, you end up with this thing that looks ugly, but it's got all the future value stuff embedded in it. And it's just a bunch of CCPs. And even this ugliness is like overstated, because we're going to compare this in estimation to say VK minus 1, because I'm deciding whether to change the state or not. And a bunch of these terms over here may cancel out anyway, okay, depending on what structure you place on it. But the point is this is all quite simple, conditional on having the choice probabilities. All right. So that was so in terms of estimation choice probabilities and simple functions of the flow payoffs, instantaneous payoffs, and the transition probabilities. So probability that I'm going to decrease the state, we've got the VK minus 1, plus I have to pay the cost. And then EXP of just doing nothing, which is staying in state K. And this is why I was saying that things may actually simplify quite a bit when you take those differences between VK minus 1 and VK. So all you're going to do is substitute all that stuff in. If choice probabilities are estimated in the first stage, you're set. Okay? All right. So another thing, and again, I chose the nice minus 1 for the choice. Keep meaning to update that. But consider a bus replacement engine problem where K denotes mileage. And we can just keep it simple, where mileage is going to increase by 1 at some rate that depends on the current mileage state. Choice is to replace the engine, which resets the mileage or do nothing. and then there's be some cost of replacement. Well, I'm immediately just going to knock out the Emax term. That's what this minus lambda log probability of doing nothing does. Okay? It's all about, the real problem is, how do you deal with this thing? Okay, so now the state's gone up in terms of mileage here. The agent has no way of making the state mileage go up. How can we make this work? Well, we can link VK and VK plus 1 through the replacement probabilities in this state and in this state. Okay? And that's going to knock it all out. Now, here's what I really, well, maybe I'll hold off on that for a moment. So what we know is VK plus 1 can be expressed relative to V0 through those ratio of those logit probabilities. So VK plus 1 equals V0 plus the switching cost, the cost of replacing, plus the difference in the log probabilities, given that you're in that state, K plus 1. VK, same thing, except now it's the log probabilities of switching and not, of replacing engine and not, in state K. So I can rewrite it, because they're linked through V0, so that VK plus 1 equals VK plus a bunch of replacement probabilities. Okay? That means I can substitute that expression in for VK plus 1. I'm going to plug it in right here, and it's going to have a VK on it, right? And when I substitute that in, I'm going to have a QK times a VK plus a blob of CCPs. The QK times the VK, the QK's part's going to cancel out there, and it's all just going to be over rho. Okay. So what you end up with is rho VK equals flow payoff minus that log probability of doing nothing. That came from the Emax. And the rest came from the fact that nature may move that state up. So the key is, whatever nature does, you got to be able to make some decisions to undo that. And if you can do that, then you're set. And it's actually easier to do that because nature's not going to keep doing stuff in this continuous time setup. Okay? The other thing I like about this sort of setup is, if we think about the renewal action in the context of the making the decision each year, in order to get the CCP estimation to work there, you're effectively going to normalize the value of replacing, normalize the future value term relative to the value of replacing the engine. And you're going to do that both for the path that began with not replacing the engine, as well as the path that began with replacing the engine. And you may not see that many times where they replace the engine twice in a row. In this setup, at the end, in the limit, it's still going to come down to that too, right? But fundamentally, you're looking at the probability of replacing the engine in say K and K plus 1 without having to link through having to replace the engine twice in a row. Go for it.
Clarifying question, I lost track. In this setup, is the engine replacement opportunity, is that its own Poisson arrival process relative to the change in mileage?
Yes. So
you have
dictates
stochastic change in mileage in this, or
so the Q's, which are here, that would be the rate at which you replace the mileage.
Got it. And then the lambda is the opportunity to replace.
Exactly.
Got it.
And we could have had this be like it goes up 1 or 2 or whatever, I just kept it to just going up 1 for,
Right.
we would just throw in more CCPs if it could have gone up,
Got it.
up by
Thanks.
more than that. And here's the other difference, and this comes back a bit, because the finite dependence in that discrete time version, unless you had a terminal choice, you always had to take a difference in value functions at the estimation stage to make it go, right? Here you're getting the difference in value functions up front without even needing to do the difference at the estimation part. Everything gets written because you're working with the value function itself, okay? All right. So no questions on that. This all makes perfect sense.
Just as a technical thing, if I can choose to replace at any point in time, replacing would be triggered along with Q. I would have a threshold where I would, like, when I get a Q shock, I would be taken to a mileage where I decide, all right, now it's time to make a decision.
And that
like,
almost
does-
sort of works
does-
in the context where there's no error, effectively, right? Because
Yeah.
there's like a threshold mileage, at which point I'm going to
Yeah.
replace. And that's actually, I think, the analog. You know, like if you think about search models, you don't have that preference shock, and you end up with a reservation wage. So if it's above that, I take it. Otherwise, I don't. In this context, there'd be a probability of taking that job, even if the wage was lower than your current job or higher. So the advantage of putting these errors in here is it smooths out those probabilities. It allows for you to go to different parts in the state space that your theoretical model would have actually ruled out,
Yeah,
but that you might actually see in the data.
Got it.
But you're right that, you know, the problem with the continuous time, and we got some pushback on this, is like as soon as you start thinking about when people make decisions, it's like, well, why can't I have them make a decision every second, you know, whenever they want? Why don't I just endogenize when they make the decision? And my counter to that's sort of weak, which is we're perfectly comfortable with having people make decisions on January 1st of each year and having that be the only time they can make a decision. I mean, I think that's, I mean, what got me, not to pick on IO, but, and now I'm going to pick on IO. I got interested in this because of the dynamic games literature, okay? So the way this literature often works is all the firms move at once, and then you see, crap, I just put in a grocery store and so did Walmart. I'm screwed, right? But I can't do anything for another year. And then I leave and, oh, I wouldn't have left. Walmart actually left, you know? In continuous time, you know, you might actually, the way I would think about this happening is you might see in a particular year times where Walmart entered and a bunch of stores exited, and another time where Walmart had entered and a bunch of stores had come in. In the first case, Walmart probably entered early in the year, and then firms responded to that when they had the move arrival to get out. In the second case, the firms entered, the other supermarkets entered early in the year, and Walmart wasn't there. Then Walmart came in at the end, and now they're going to be getting out quickly. That actually, and man, I'm getting ahead of myself, that actually gets into how you would think about the fact that you only see yearly data, but the underlying process is actually a continuous time one, and those actions can actually reveal when in the period that the events actually might have occurred, would be the idea. Go for it.
Do we actually require seeing the order of events at like such a fine time interval? So like in the Walmart example, is it appropriate to adapt this continuous time model with all of these advantages and stuff that you described in the typical discrete choice or discrete time data set one is likely to encounter of one Walmart grocery store and one or zero other grocery stores, et cetera. You see my question here?
Oh, totally.
Okay.
So my practical response to that would be is I am as comfortable setting lambda to be 1, which would be roughly 1 move a year, as I would be with saying they're making a decision on January 1st each year. And if you give me that, then the fact that you've got the aggregate stuff doesn't matter. There's going to be a set of things that there's no way you could be able to identify, like if you're going to have that lambda be so fast, then if the period's too long, you can't really, it's going to be harder to pick it off. But given the example I just told you, I think that's exactly why the fact that we see within a year particular patterns, we might be able to tease out, when things happened. We can sort of, in a way, back out what the probability, like for any given, let's say I've got a yearly data, after I estimate my model, I could back out what the probability was that a move happened in the first 6 months versus the second 6 months. In a single agent case, it's very easy to do. I think there'd be some little bit more hand waving when we got with regard to multiple agents, because then you got to worry about all the combinations of moves and such happening there. But I think you could effectively integrate out over that. Go for it.
One quick follow-up is it seems like the time interval at which you observe state variables, such as, say, inflation, is like a main state variable, I don't know, for Walmart grocery stores. Whether you also, the interval at which you observe that relative to the interval at which you observe the choice variables is important, right? So whether you observe inflation monthly versus annually will.
Sure, and what sort of, you probably are going to put some structure on it to make it work. I think these things get really tricky if we're going to think about things like moving around Brownian motion type of stuff. You want it to be rates that take you up and down states. That's putting some structure on the problem, and now you're sort of weighing those trade-offs with having it be the inflation rate is this rate when I made this decision, and then boom, when I make my next decision, it popped up to some other level. You've got to put a little bit more structure on the problem then. I think that's why, honestly, I think that's probably why it hasn't caught on in the same way. But I sort of feel that it's sort of like all these models have bad assumptions. And when I first started writing my dissertation, it was like, I'm going to have correlated preference shocks that follow some AR1 type of thing. I just kept telling myself, this independent error assumption is not too bad. And it's fine, because you have to make approximations. The question is that worse than what the alternative is? And some of these things, it's hard to gauge. But I do think, I'm an IO economist. The only time I can get invited to like Princeton or MIT is as an IO person. They won't have me up as a labor economist, but I'm not really an IO economist. But I think that's a really promising area, is continuous time games, for the reasons that I just mentioned. Though IO guys should feel free to push back on me. Okay. So keep in mind, now this is the part where Erasmus gets me to start laughing at me as someone who works with continuous time all the time. I came at the continuous time stuff from the discrete time. So all this, the likelihoods and hazards were foreign to me. So thinking about going step by step through what those likelihoods look like in this case, my classes tend to find that helpful, and it's helpful for me. And actually, if you go, I posted it late, but there is a problem set that's a really simple continuous time problem set where you actually see people moving and continue, you actually see when the move arrival came and such. And that can get you started in terms of building up those tools. that has the problem, that has my code, that sort of the shell program, it calls a likelihood function, and then I actually post the code that generates the data. Because I think that's something that people should do a lot, is generate your own data to make sure you're thinking about the problem correctly. Of course, you could screw up the data generating process and screw it up likewise in the code in a way where you can't find it. But nonetheless, I think it's a useful exercise. So for students in my class, we actually walk through my MATLAB code. I didn't warn you about that, so I'm not going to do that here. Okay,
So
go for it.
it looks like in this particular application, I think it's useful to think of empirically, you then have a data set where you see replacements happen, say after 30K or something like that. But there's a range, like 0 to 30K of mileage, where you just never see a replacement being done. So in that range of 0 to 30K, it looks like if I take this, I can't link those states to each other through the engine replacement, right? They're not communicating with engine replacement, except sort of through the nature taking you up above 30K.
Yeah.
So how
I'd have
does
to
that,
think about how
work
to-
in this case?
Sorry, say it again.
So how does that work?
So I think that does raise big identification. I think you'd have to be getting it off the structure of the problem.
Right,
So
because
you-
now
so
it,
you
look,
have
it
like
looks
a-
like you're going
a
to have
U
to
of
start solving the
mileage.
value function problem, right?
What?
Now it looks like you're going to have to start solving the value function problem.
Potentially, I think to get the parts associated with that, with the mileage
With
in
the 0
that
to 30.
range. So I think you can link the ones above that range to 0 and get those worked out. The ones in that range, the only way you're going to be identifying that is off a functional form of the mileages anyway, right? So you say the utility of, you put down the cost of mileage is EXP of the thing, and so then I can back out what the mileages is for which they're not making any decision. You have to do that, I think, to recover it. Okay, so forming the likelihood. So what we want to think about is just denoting the probability of doing nothing in state K by the sigma 0K. So right now I'm going to work in the case where you see everything and just say, well, here's what the likelihood looks like, just so you get the idea. So with a Poisson arrival, probably the next state change occurring ends up being 1 minus EXP, and then you got this minus t times the sum of the rates, okay? Reality is, I don't have a lot of intuition for this, and if I was younger, I'd probably try to figure it out, so it's a formula for me. But that's what that is what the probability of the next state change occurring. So keep in mind, what do you see in the data? You see nothing going on, and then at time t, something happens, right? You see a whole bunch of events at oddly spaced intervals. That's what the data set I posted will give you. And then you see however the state moves. So differentiating with respect to t is going to give the density of the next state change at t. Okay? And then conditional on a state change occurring, the probability is because the agent took the action, it took action j, is going to be lambda times that probability they took action j in that state, divided by the sum of all the other things that could have happened there. Now that makes it look more complicated than it is, because if you thought about you're going to plug that in, and these parts are going to cancel. Okay? So what you end up with is just the joint likelihood of the next state change occurring at t being the result of action j is lambda times your choice probability times this EXP of those rates. The likelihood of the data is in the product of all these densities that you see for each event that happened. right? And then you take into account that they're censoring sort of at the end, right? So if your thing goes out to a particular time period, the fact that nothing occurred is still informative. All that is straightforward to incorporate into this setup. So that all sounds fine. That's when you see all those states, the timing of all the events. But if you don't see the timing of all the events, that's where the problem occurs, is how do you sort of deal with the time aggregation. So there's a trade-off, right? Because on the one hand, I think that the continuous time stuff, what time do I go to anyway? Well, I'll let you figure that and you can let me know. 50? Okay. Okay. I may give you back your 5 minutes that Bob stole. So there's a trade-off. Continuous time, I think, actually makes it a lot easier to form the value functions and all that, but then at estimation, you got to deal with the fact that you see things in these discrete intervals. Well, in any event, first is a simple case. Data observed in continuous time, including when the individual chooses to do nothing. The Q's and the lambdas are estimated in the first stage. For lambda, you just count the number of decisions and divide by the sample period. If we had to be lambda k, in that case, you'd count the number of times, the number of decisions divided by the time they were spent in state k, and that would tell you what the lambda k was. And that would actually, if you saw that data at that finite interval, you could test for whether it was related to k or not. KL, count the number of times the state went from k to L, and divide this by the amount of time the state was in k. Okay? So it's actually really simple to do in that case. And then for the structure, so I wrote down all those Poisson stuff. In the end, you don't need to do that. What you need to do is do some division here to get the lambda and the QL, and then estimate a logit or a multinomial logit, depending upon what choices are available to the agent, and you're done. So you don't even need all that G stuff I put up there if you see everything happen in continuous time, which you actually do in the thing that I posted. Though actually, I do this lecture before I don't do the CCPs in the code. We actually solve the fixed point there. The CCP, it's fast enough with because it's so simple. So point being, for structural payoffs, just like discrete time, estimate a logit or multinomial logit, where now we're plugging in for the value function itself into those probabilities. Okay. So things get a little bit more complicated, obviously, when you've got time aggregation, what the data is recorded quarterly or yearly. You don't actually see the sequence of moves. I'm not going to have time to get into this, but you can use the transition matrix, which is the probability of certain things happening, of the states moving from one state to another over an interval. There's two ways to think about it. There's it's called the matrix exponential, which I've never done, but my co-authors who are a little bit more math savvy than me, they're actually, MATLAB will do that for you. For me, coming at it from dynamic discrete choice in discrete time, I like to think about it in a little bit different way, which is think about integrating out over the moves that could happen. Okay? So it's log of the likelihood that you see that data, and just like you integrate out types, unobserved heterogeneity types, we could draw a sequence of moves and plug in the corresponding probabilities associated with that. That's where having it be lambda, not lambda k, is very helpful, because then if it's just lambda, you're sort of good to go. Even then, in the game's context, it's tricky because the number of players. But in that case, you've got the state-independent Poisson process dictating when moves occur, and then a Markov chain, which gives the probabilities of moving from one state to another conditional on a move opportunity. Once you do that, it works out quite nicely because you're still working with this. Now we know when you've moved. We've integrated out, so we know how to calculate that probability. That's really, in some sense, what the matrix exponential is doing. I've just done it by hand so that I understand what's actually happening as opposed to that matrix exponential thing. Okay? All right. So I think if I was on track without Bob's 5 minutes, it would be over right now or not? Because I can talk, I can preview, this is an actual pause, or I can keep talking because I can preview what we're going to do with the search paper. I don't care either way. Go for it.
This is related to time aggregation. So if you go back to CCP, if you don't see when people move, how do you get the... I can see how you can construct the likelihood, but how do you get the sigma if you don't know when people make reaction?
Yeah. Yeah, that's actually, that would take a little while to get. I mean, the way I want to think about it is that, notice I also didn't even touch on unobserved heterogeneity as well. I think a lot of that stuff can almost get resolved in a first stage. And you'll see that with the search paper. And if you're not going to be there for that talk, we can talk after that. But with the search paper, you can actually get, that's one where you don't see you don't see the turned down offers. All you see is that somebody moved. That's still better than what you normally have because you might still have like the exact date they moved, but you don't see the turned down offers. And there we can recover everything quite easily. But it's not like you just get the CCPs and then you're set. You actually get other things first that fall out from that. But in the restud paper, we actually do get those things in a first stage. We don't do the value function stuff. But that takes a little bit of a while to explain. So I think I will stop there because it would there's some notational lifting to get to the search stuff. And then I'm going to steal 5 minutes of Chris's time, unless Chris wants to see the minutes. Keep going? Okay. All right.